Okay, so this is a continuation of our independent means t-test, and we're going to be looking at diagnostics. And because we have two separate groups, two independent groups, we have to look at ensuring that our groups, if the null hypothesis is true, they're essentially drawn from the same population. So therefore, we assume that the two groups, the variance for the two groups is relatively equal. And for our smaller sample sizes, we want our groups to be normally distributed. So there's two things we have to look at. Normality, is the data normally distributed, and whether the variances, the two variances are relatively equivalent. So if the data is non-normal, typically it'll be either a negative skew or a positive skew, as we see in the figure on the screen. Okay, so I have an example data set. It's volunteer hours for males and females. I'm going to say it's the number of volunteer hours during a given week. And I want to determine if there is a difference in the mean number of volunteer hours based upon the volunteer person's sex, male or female. Okay, so I want to run an independent means t-test. Now, what's here? My ends are unequal, and I have to, basically I got to do my diagnostics. And first thing I'm going to want to look at is my data normally distributed, and then I'm going to want to look to see if my data is, if the variances are relatively equal. Okay. First thing is, this is the first time we've seen an unequal number of participants in a study. So when we have that, all things being said, because the ends are unequal, the practice is to not use the standard error calculation that we've used up to date so far. And the standard error calculation that we've used is the variance for group 1 divided by the n for group 1 plus the variance for group 2 divided by the n for group 2. What we do is we create, and when the ends are unequal, we want to pool the variances so that one variance, in a sense, is each makes a proportional contribution to the standard error variance. And the calculation we do is we have what's referred to as a pooled variance. So when the ends are unequal, we basically take the sums of squares for the two groups, add those two sums of squares, and divide by the total for the 2 degrees of freedom added together, df1 plus df2. So what we're really doing is we're creating a pooled variance, like we're almost lumping them. What we're essentially doing is taking each mean, and we're lumping the two together to create a what's called the SP squared, which is the pooled variance. And then when we calculate the standard error, instead of using the variance for group 1 and the variance for group 2, for both groups, we use the pooled variance. We use it twice. So we take the pooled variance divided by n1 plus the pooled variance divided by n2. Right. So then we would run our t-test. Okay. So with unequal ends, we use the pooled variance, and we'll walk through an example in a sec. Okay, two assumptions, as I said before. The variables have to be, if the n is small, we have to be concerned about make sure that our two distributions are normally distributed. We know that two tenets of the central limit theorem. One tenet is, the first one is that the sample mean is an unbiased estimate of the population mean, and if I were to run for the distribution of sample means, the mean of that distribution is equal to the mean of the population from which the distribution of sample means was created, right? So if I were to run my study 200,000 times, and I have a sample size of, 15, if I calculate the mean for that 200,000 sample means, it'll equal the population mean from the population individuals the samples were drawn from. And the second tenet of the central limit theorem is that the standard deviation for that distribution of sample means is equal to the standard deviation from the distribution of individuals divided by the square root of my sample size, or the square root of n. The third tenet of the central limit theorem is, if my sample size is roughly greater than 30, I don't have to worry about whether or not the population of individuals is normally distributed, or my sample is normally distributed. because when the sample size gets large enough, even though the population from which the samples are drawn from is not normally distributed, for large sample sizes greater than 30, the shape of the distribution of sample means will be normally distributed. So that's the third piece to the central limit theorem. But for smaller sample sizes, say less than 30, we have to worry about whether the data is normally distributed. And the second piece is I want my variances to be roughly the same for my two populations for my independent means t-test. And that's referred to as homogeneity variance, and we'll get into that calculation in a bit. Okay, so we saw skewness is there's a measure for skewness. I'm not going to go into it in any detail in terms of the calculation. I'm not going to make you calculate it by hand. It is that's a positive skew here, where the data tails off in the positive or right direction, and then the negative skew, it's the opposite side. The measure of skewness is simply instead of where we used to do the squared deviations from the mean, well, the skewness measure is not the squared deviations from the mean; it's based upon the cubed deviations from the mean. So not only we don't just square it, multiply it by itself once, we do it 3 times. And what that does is it brings the minus sign back into the equation. And that measure will tell us basically to what level of skewness. If the data is normally distributed, the cube values will be essentially 0. Okay. To check for normality, we use the Descriptive Stats Explorer from SPSS, and then most of what we do this semester will be in SPSS. So I pick up the Explorer, my dependent measure is volunteer hours, my factor of the groupings is sex, and then I get my output. My indicator I look at is I'll look at my, I can look at the variances, and I can see very clearly from the variance for the males is roughly 4, well it is 4, and the variance for the females is 14.4. And I can see that in my, this is referred to as a box and whisker plot. The box represents the quartile, so the median is the black line. The third quartile, or the 75th percentile, is that line, and the first quartile, which is the 25th percentile, is this line. So the box represents the values that are between the 25th and 50th percentile. The whisker at the top is the max, and the min is the whisker at the bottom. You'll often, and we'll see this in a bit in the next example, we'll see an asterisk for outliers. Those are extreme values. And an outlier in SPSS is any data point that is 1.5 times the width of this blue box here. And the blue box represents the interquartile range, which is the difference between the value for the 75th percentile, the third quartile, minus the value for the 25th or first quartile. And any value that is 1.5 times greater than if that distance is more than 1.5 times greater than the width of this box, then it shows as an individual point. And we'll see that in a sec. Okay, just to run it through SPSS. So analyze, descriptive stats, explore. And my factor is sex, my variable is, and this replicates what's in the PowerPoint slide. And there we go. Okay, so that is, so I can see that my data is, and then for my measure of skewness, I have it here. And my ballpark for whether a data is skewed or not, I'll start seeing individual points that are 1.5 times the interquartile range from the median. But the skewness measure, what I can see is if this value here for skewness, if it's more than double the standard error, so in this case, if my skewness was negative 1.7 or so, I would start getting concerned. I would be concerned that my data is not normally distributed. But in this case, my data is normally distributed, so I'm okay. But my variances are not equal. Okay. Now, if my variances are not equal, which in this case they're not, We'll see in a sec how we determine that. We do a slightly different t-test, which is referred to as Welch's t-test. And what it does is, for that test, we use the same standard error calculation we used last semester, which is basically variance group 1 divided by n, variance group 2 divided by its n, and add them together, take the square root. But what we do is we adjust down the degrees of freedom to make it harder to reject the null hypothesis. And I'm not going to go into any details in terms of the calculation, but this is what it looks like. Okay. Now, to test for whether our variances are the same or not, there are two tests. The simplest test is Hartley's Fmax, which is simply the largest variance divided by the smallest variance. And there is a table on Blackboard. I'm not going to go into it in any detail. I just want you to be aware that you'll see it. It's a rough and ready measure. The problem is it doesn't. When it's looking at homogeneity variance, it's influenced by the degree of normality. So you want some kind of a measure of variance differences that is relatively unaffected by the shape of the curve. And that one is Levene's test. I'm not going to go into any detail, but SPS uses the Levene's test for variance homogeneity. The null hypothesis is the variances are the same. The alternate hypothesis is the variances differ. So in this case, when I run the test, I reject the null hypothesis, and I then conclude that if I do reject it, that the variances are not the same. And this you'll see in the output in SPSS. Okay, so that's the hand calculation. This is what I'll come back to in a sec. This is what I get in SPSS. So, when you look at your SPSS output, you'll look at the first thing you're going to look at is this two boxes right here, Levene's test of equality of variances. It gives me what's referred to as an F observed, and it gives me a significance. The null hypothesis is the variance is the same. The alternate hypothesis, the variance differ. If I reject the null hypothesis and this value is less than 0.05, I therefore conclude that the variances are not the same. And in that case, I go down and run and do the t-test for variances unequal. And that I'm using the Welch's t-test, where you can see where the degrees of freedom are adjusted down. So here the degrees of freedom is 11 if the variances are equal. There's no adjustment down. And here for the Welch's test, the degrees of freedom are reduced. You'll also see the standard error is slightly different. The standard error, when equal variance is assumed, is based upon the pooled variance, whereas with the Welch's test, the standard error is based not using the pooled variance. And the not using the pooled variance is what we did last semester. Okay. I have the calculation done by hand in Excel, and you'll notice the difference in the p-value. So this is the second row of the SPSS output, and you'll see here that my p-value in Excel is 0.0534. My p-value in SPSS is 0.052. Excel is not the best for statistics, because what Excel does is it takes the integer value. So it takes what it does is it takes the degrees of freedom, and it takes the degrees of freedom and just takes it as an integer, as a 7. So it says, okay, it only runs with integer numbers, so it can't complete the p-value for a degrees of freedom that has decimal points to it. So in that case, it just says, okay, just take it to 7 and treat the degrees of freedom as the integer value, just 7, and calculate the p-value. And that's exactly what it did. So Excel doesn't quite do it the right way. Okay, so just to demonstrate in SPSS, so analyze, compare means, independent samples. My variable is sex. I want to know what it's grouped as. So if I right click over sex and go variable information, it's coded as a 0 and 1. So define groups, 0 and 1. Continue, and my test variable is volunteer, and I go OK. And this replicates what I just showed you in on PowerPoint. And then you also have your this is the data, doing it by hand. And what I see is I've done the calculations for the adjusted degrees of freedom to replicate what's in SPSS. I'm not going to force you to do this by hand, but you can walk through it yourself, and you can then see why you can see the difference in the p-value. And you can also see here in the unequal variance, that first row of SPSS, the standard error is 1.643, and here's my 1.6436, 1.64356. And also just okay, there we go. And it's using the pooled variance. So this first row of SPSS, if this had been greater than 0.05, I would have stayed with the first row. In that case, there's my standard error. It uses the pooled variance, whereas with Welch's t-test, it doesn't use the pooled variance. It does it the old way that we did it last semester, so it's not pooled. Okay, and that is, so if my n's are small and my data is normally distributed, that's how I run a t-test. And my focus is on whether or not the data is normally distributed. In this case, it is. But what I did find is my data is the variances are not equal. So I had to go to the second row of the output from SPSS. So the next thing we're going to do for this class is looking at what do we do when we want to run a t-test and the data is not normally distributed.